Welcome to another one of the Landscapes Live seminar, part of the seminar series. It's my pleasure today to introduce Odin Marc from the CNRS, or the University of Toulouse. And today he's going to talk a bit about his research, looking at what do we need to better constrain spatial and temporal occurrence of rainfall-induced landslides. Odin has agreed that this particular talk can be recorded, and it will be put on the Landscapes Live website as usual. Yeah, Odin, when you are ready, take it away. Odin will talk for about 40-45 minutes, and then we will have time for questions. The chat will be open at about 5 to 10 minutes before he finishes speaking, so please get your questions ready. And then the Landscapes Live team will moderate the chat and ask the questions of Odin. Okay, thank you very much.
Yes, thank you, Lizzie. Thanks everyone for joining and coming to see this seminar. Thanks for the organizer also to continue to have this webinar on Zoom every week. It's really nice. And yes, so today I will show you some recent work, ongoing work also, and work I've done since I am in Toulouse, about what do we need to better constrain spatial and temporal occurrence of rainfall-induced landslides. And so it's work I did with colleagues in the JET, Marielle Gosset, Romulo Oliveira, Cathy Burrows, and also abroad, so Rob Emberson in the NASA, some colleagues in Strasbourg and Japan. Before I start, I can describe a little bit this image that some of you have been seeing while they were waiting here. And it's landslide caused by a large typhoon, the Morakot typhoon in 2009 in southern Taiwan. So it's an image from space where you can see that almost all the landslides here that are these gray scars here on the hill slopes in red in this fake color image. They are occurring at every scale, almost everywhere. You have some that are very large here, almost 1 kilometer long, and they cause a lot of change in the landscape. Look, these landslide dams, large elevation in the river. And this is one of the strongest events on record for rainfall-induced landslide. But when we look at the global picture, we can also find that mountains are really driving all the global erosion and sediment budget. And I quote a sentence from the conclusion of Larsen and colleague here, where they say that 50% of the total denudation and 40% of the chemical denudation occur on the steepest 10% of the earth. So in the mountain ranges, basically. And they found this by combining a large database, global database of beryllium-10 erosion rate in catchments with their topographic properties. But also, even if we don't look at these specific numbers, if we want to have an idea, we can think to the classic work by Milliman and Farnsworth, looking at sediment fluxes from main rivers. And you can see that if you sum the sediment coming from Southeast Asia, so Japan, Taiwan, New Zealand, also Tibet and the surroundings, and the one from the Andes, you have already more than half of the sediment export from the world. So it's much more than what if you compare very flat areas like Siberia, Canada, Africa. So really the mountain ranges are the key place if we want to understand global budget of erosion and sediment. And in these places, there have been a series of work that shown that landsliding is a key agent in producing these sediments. For example, in New Zealand, in the Andes, in the Himalayas, there was work showing that if you sum and if you estimate the budget of landslide, it matches well with the long-term erosion rate and the sediment production. And also beyond just the aspect of budget, landslide produce sediment and then the river export them or erode through them. There is a fundamental question about the coupling between river incision and the sediment delivery and transport through the tool and cover effects. And in this problem, the landslide is a key problem. There was nice work by Egon, for example, but there need to be more work to understand this, how the landslide and the river are coupled. This was a bit a catch-up for the geomorphologists in the audience. But then why is it so complicated to predict and understand landsliding? Well, it's because you can simplify landslide as a force balance problem on a potential failure plane, let's say on a hill slope here. But then this force balance is controlled by many effects, local ground properties, but also trigger process like earthquakes or rainfall. And each of these terms actually are complex and difficult to measure at fine scale, because you have on a landscape, you have hundreds of different hill slopes, thousands of hill slopes that can all have different ground properties. So they can have different strength, cohesion, friction, different slope, different thickness of the regolith, or etc. But then when you think to the acceleration that disturbs the force balance during an earthquake, it will itself depend on the magnitude of the earthquake, the source depth, the source dynamics, wave frequency. All these are important research questions in seismology. And the problem is the same for rainfall and how it affects pore water pressure. It's a large set of questions in hydrology, how we need to understand the rainfall intensity, duration, the intensity and moisture. And also this trigger effect and local ground properties effect, they are strongly coupled because the ground properties influence hydrology through preferential drainage, for example. And because the ground properties also influence the recorded acceleration and how it affects the force balance through site effects or through ground damage. So one approach could be to try to focus on try to understand the link between the trigger and the landslide, if we want to have later predictions, by somehow getting rid of the variability of the ground properties, by averaging out this very large number of variables and that are each very variable at fine scale. So we can do that if we have large amount of landsliding, and there was pioneering work by Patrick Meunier in 2007, 2013, where he could show that the landslide density can track the ground shaking during an earthquake. So if you look at here, how much % of a landscape is covered by landslides, and you look at that in different bins where we could record the ground shaking, the peak ground acceleration, you see a linear trend, and you could see that for many earthquakes. If you go further than that, you can integrate this shaking recording, for example, and try to relate that to the total amount of landsliding and to the total area where they occur. You have here a map. So this is a slope map of the Wenchuan area. You have all the landslide caused by the Wenchuan earthquake in yellow. And you have a model here in green along the fault. And in red, you have the actual area containing 95% of the landslide. So you could see we could reasonably match a prediction of how far should be the landslide from the fault. And if you have large amount of landslide, what you can also do is not only look at how much they are, but what's their size distribution. So if you look at the probability density of the area of the different landslides, and you look at groups of landslides that are in specific area of shaking, you see that the landslide population in low shaking area have much less large landslides than the one at high shaking area that extend much further and that have also a different decay exponent. So all these examples, and there are many more, and these were just some of them where I've been contributing, have been developed for the earthquake induced landslides because there were many catalogs of very large events with thousands or tens of thousands of landslides. It came a bit later for the rainfall induced landslides. And what we had for a long time, and this is first of all a review of this type of traditional approach, I call, of rainfall threshold, was mostly the case for the rainfall induced landslide, but we looked at a few examples of landslides that were precisely dated so that we could know exactly what was the rainfall before their occurrence. And if you plot each of these points, here, these dots here are one landslide event, and you could see that you need a minimum intensity and a minimum duration of rainfall before you have landsliding. If you have not enough rainfall, nothing happens. If you have a very intense and very short storm, or if you have a very long storm, even if it's not very intense, you will have landsliding. But on this representation, we can try to find a threshold that is useful in itself, but we don't know really what's the difference between a landslide event here, whereas there is only 10 millimeter of rainfall recorded, or one here at 100 millimeter, or one here at 1000 millimeter. So in other words, how is the magnitude of landsliding changing beyond the threshold? And or also in another way to say it is it enough to know that landsliding is likely when you are above this threshold, but when you don't know where it will occur in the landscape, how many landslides, how big they will be, etc. So what I will try to do in the first part of the talk is to show how we can relate the landslide patterns to rainfall pattern in large events. And then I will continue looking at how the rainfall product derived by satellite can be useful for this approach. And then in the last part of the talk, I will talk first of the temporal occurrence of landslide in cloudy areas, typically during monsoon seasons, and discuss the problem of deep-seated large landslides and how they may need to be considered in a different way. So let's start with looking at how detailed rainfall measurement can help to understand a large landslide event. And this is a case study based on the typhoon Talas that occurred in 2011. You have the view of the typhoon here, and the Japan coast is here. And the key peninsula is here where many landslides were triggered. So we have, I show you here the landslides that were mapped based on pre-event and post-event imagery. So it's only landslide caused during the typhoon. They are in black in this three figure, in red here. And on the bottom plots, you see the total rainfall measured by a rain radar on the ground during 48 hours during the typhoon. And you see it can reach more than 1 meter. So it's really a lot of rain in just 2 days. And it's well distributed across the peninsula. On the topography here, you see that we reach more than 1,600 meters on the range, in the coastal range. And if you look at short pulse of rainfall in the maximum rainfall amount in 2 hours, you have also very important rainfall, almost 200 millimeters, but mainly located on the coast. But what is important here, interesting, is that whether you look at long time scale or short time scale, it doesn't really explain the pattern of the landsliding. You see that the landslide is not really homogeneously distributed on the range or located only on the coast. You have a lot of landslide here in this valley, and very few landslide in this valley or in this one. So why is that? Well, we could think it could be because there are differences in slopes, also in the susceptibility or in the strength. And if we look at the DEM, we don't see any real difference, and the slope distribution is similar across these areas. And if we look at the lithology again, there is a different lithology on the coast with volcanic rocks, but in the center of the peninsula, it's all a melange, and there is no real difference in the lithological map between this valley and this one. So there could be maybe over variation in regolith properties. And the idea is that maybe the properties of the soil of the regolith of the peninsula could also be related to the climate, especially to the extreme climatology. This is related to the idea of landscape coevolution that was suggested through various geomorphological modeling work. But if you have frequent intense rainfall, then you will have frequent landsliding that will limit the soil thickness, for example, or that the soil will change in terms of properties to be able to remain stable when you have these important storms. So maybe we can use a regional map of extreme rainfall as a proxy for the regolith susceptibility to landsliding. So to do that, we had the opportunity to use 26 years of radar data in Japan. Therefore, all across the area, we could map the maximum annual rainfall. So you have here a cumulative distribution function of rainfall intensity, for example. And when you have all these annual maxima, we can fit a general extreme value distribution. And with this fit, we can estimate the return period. So intensity of the rainfall, or the total amount of rainfall that comes back every 10 years, 20 years, etc. So here we focus on the 10-year return rainfall, but we showed in this work that 20 years would be similar. And so what we did then was to combine the total rainfall during the event at a given time scale and the 10-year return rainfall to create an anomaly. So we normalize the rainfall during the event by the climate or the extreme climatology, and we obtain an anomaly here at 48 hours or at 2 hours. And what you can see is that the 48 hours the anomaly is very large and very well located in this valley where you had all the landsliding, whereas it's quite moderate on the other part here, and it's very weak in this part here without landsliding. And the short time scale, you have still a very large anomaly only on the coast that may explain these two clusters. So with this normalization and this anomaly, we had a much better mapping of the landsliding, and we could also quantitatively correlate the landslide density in % with the rainfall anomaly, as it was done, I showed you before, for the shaking during an earthquake, for example. So all this, you can find it in a published work in JRL in 2019. So I will not go more into detail for now on this work, but just to summarize, for this large storm, at least, we could show that the rainfall anomaly tracks better the landslide density than the total rainfall during the event. And the hypothesis is that this is because the regolith properties follow the spatial pattern of the extreme rainfall. So when we normalize by the past rainfall, we somehow account for various states of the hill slopes, and therefore we better predict the landsliding. So, of course, this was done with a huge amount of data, 26 years of rainfall radar, so high resolution in time, in space, and very long record. So would we be able to use the same methodology in a data poor environment where, let's say, in the Andes or in the Himalayas? And the question is, to test that, what I have been working on is to check if the rainfall products derived by satellites could help us to apply the same methodology and therefore to understand landsliding even when we don't have so much in situ rainfall measurements. So just a quick recap on how the rainfall is estimated from space. So the rainfall estimation is due to a constellation, the GPM constellation, and it's many satellites, and one of them, the GPM Core Observatory, contains both an active radar that does the same thing, measuring the distribution of droplet size in the clouds, like a rain radar on the ground. But this satellite also has a passive microwave brightness sensor, so that this passive sensor can be calibrated at the same time when the radar is measuring the rainfall. And it can be used to calibrate the rest of the constellation, where all of the other satellites here are acquiring only passive microwaves. And of course, as you can see in this image, as all satellite pass, you may have gaps in between the overpass, especially at high time resolution. And so in between the overpass of the satellite, we use geostationary infrared that is acquired every 30 minutes on all the globes to interpolate, based on cloud movement, interpolate the microwave measurements, and also to estimate based on the infrared measurements whether or not it could be rainy below the clouds. And in the study, I've used 3 long-term products that are available from 2000 to now at high resolution. So it's from half an hour to 3 hours, and it's every 0.1 degree, so every 10 kilometers. And it's GSMAP, the Japanese product, iMerc, the American one, and MSWeb, that is an hybrid product that combines satellite models and gauges. And so what did I do? Well, I looked at the 20 years of data, I resampled it at a given time scale, and then I computed the 10-year return rainfall based on the meta-statistical extreme value theory. It's another approach than the general extreme value, but it gives similar results. And here you can see again the key peninsula, you recognize it on the map, and you have the rainfall in millimeter during the event at 48 hours. You have the 10-year return rainfall here, and then you can combine these two to get an anomaly where you have contour here of where the anomaly is above 1. And you can see that the anomaly is not really exactly where the landslide are, but at least we did retrieve a large anomaly overlapping with the landslide at the right time. So this was with one satellite with the GSMAP product. Of course, we have 3 products, and we see that they don't yield the same result. So here we have the same thing, the anomaly between 0.5 and 2. And you see GSMAP has a large anomaly on the landsliding. MSWeb has almost no anomaly. There is a weak anomaly very far here on the coast. And iMerc has something much weaker, but yes, with some anomaly here on the coast and in the range. And this is for 2011. We can do that for over years in the same area. And in this area, there was also landsliding in 2004. We see again that there is difference in results. Like here, it's better retrieved a strong anomaly by iMerc. But what is interesting is also to look at years where there were no landsliding to assess whether or not the satellite product retrieved a strong anomaly or not. And obviously, if they retrieve a strong anomaly, it's a problem because it means somehow they overestimate the rainfall, or there may be some type of, or we could not use at least this anomaly map to predict or make some type of warning or hazard alert, because this would be a false alarm. And indeed, at least in some years, I don't show you all the years here, but in some years we do see that the satellite record relatively large anomaly on the ground, whereas there was no landsliding reported. So this was just the example of the application for Japan. But obviously the point of doing this with the satellite is that we can do it everywhere. So we have collected a lot of landslide triggered events, triggered by a given storm that we could fairly well date. This is, some of them are published in a paper I did in 2018, or a paper by Rob Amberson, a recent one in NHSS. And you can see that they go from the Caribbean, Colombia, Brazil, some in Africa and Italy, a lot in Japan, Taiwan, the Philippines. And for all of them, we could test whether or not we had a good match between the anomaly measured by satellite and the landsliding. So just to show you some example, in some case, we have a fairly good performance. And again, we take the total event rainfall. It's a 10-year return. You can see here that we have an escarpment. We are in Zimbabwe, at the border between Mozambique and Zimbabwe. And all the landslide occurred there at the edge of the escarpment here, whereas this is a flatter area. And given that there is a strong gradient in the 10-year return rainfall, when we go from the total event to the anomaly, we see that although the rainfall was less where the landslide happened than here, it was a relatively strong anomaly also. And this is very well matching the location of the landslide event. And what is interesting in this case is that this one, this anomaly was the largest anomaly in the 20 years of data. So it kind of makes sense that the over years were much weaker and therefore they didn't cause landsliding. And this type of relatively good or fair performance in terms of spatial co-location could be obtained for about 2/3, 70% of the 20 cases. For temporal agreement, meaning that the anomaly causing the landslide was the largest one, there were no larger anomaly in years without landsliding, could be only true for about 50% of the cases. And to show you some cases where it doesn't work, we have some events where we don't retrieve any anomaly. This is the case here in Italia, and this is true for the free products. We have some case where we find there is a rainfall event, so that is a bit larger than what happens in the surrounding, at least at the time here in Japan in 2014. But when you convert it in anomaly, when you normalize for the climatology, it completely disappears. So somehow maybe there is also an issue in the way we compute the anomaly from this satellite record. And then in some other cases, we do find some anomaly, but it's really very far and there may be many false alarms. So again, not a very good result. And many of these poor results were also occurring for relatively short events. So for short localized storms, 3 out of 4 events were missed or poorly retrieved. And it kind of makes sense because it's the probability that you had a strong satellite measurement, not only the infrared, but also the passive microwave or the active radar is decreasing as you go, as you are starting to look at much smaller scale and shorter time scale events. So clearly there is room for improvement. To show 2 more examples, one thing is here looking at the different total absolute rainfall for Taiwan for the Morakot 2009 event that I show in the introduction in the first image. You have here all the landsliding, massive landsliding in the south of the island. And you see that the pattern of event rainfall is very strong to the south for all events, but the amount of rainfall is very different. You have only about 500 millimeters in average in the south for iMerg and GSMAP, whereas you have more than 1,000 meters for MSWEP. So clearly, if you would not do a normalization, it would be impossible to find a simple threshold to determine whether or not you should give an alert, whether or not you have a risk of landsliding, because the absolute value of the satellite are often strongly biased. When you normalize by the long-term climatology that comes with at least in parts, the same bias, then you remove part of the bias and you have a variation that is much more contained between 0.8 and 2. Even if, as you see, the spatial pattern is very different. So if you would try to associate an amount of anomaly to an amount of landslide, you would have a different prediction with these different products. So how to improve these products? Well, we give some proposition in this paper in Earth Interaction that should appear soon online. We show that probably we should improve orographic effects. It's included in GSMAP, but it's not included in iMerg, so it should just be an inclusion in iMerg, because many of the events occur on coastal range or range near the sea, and clearly the orography is an important part. We could maybe combine the various results to reduce the variability and the noise, because we see also that some products perform better in some place and others. So maybe by averaging the product, we could have a better prediction. And the last possibility is to use maybe lightning that are retrieved by some satellite now in real time. The GOES satellite does that for North and South America. And we propose that because at least in one event in Brazil in 2011, you have the landsliding here that occurred in January with a relatively strong storm. You can see here the total event rainfall for 1 day. And when we do an anomaly, you see that the anomaly is relatively well located, but in detail, it is not able to, let's say, it's a bit offset, and there is a large cluster of landslide here, where the anomaly is very weak. Whereas when you look at lightnings recorded by the ground network, you have a large cluster of lightning here, and the lightning are also mapping quite well the clusters of the landsliding. These are all the lightning on the day, and we can also see that all the lightning occurred in the early morning of the day, just when witnesses were reporting that the landslide were occurring. So here the lightning could really help, at least in some case, because they could be correlated with the intense convective storm and therefore the intense rainfall that can cause landsliding. Okay, so this was a lot of examples of what happens with this satellite product, but I hope I could convince you that there is some potential with them, but that it's useful to not only consider the absolute rainfall, but to normalize it using a statistical method to extract extreme and the 10-year return rainfall, for example. And therefore, the anomaly could be quite well consistent with the landslide event for 12 or a bit more of the case out of 20. So it's not perfect, but it's quite good. Actually, if we remove the short event, we are more at 12 out of 15 events. So it's not so bad for large typhoon events. And we will continue to work on this, especially trying to see if the predictive power is maintained when we look at nowcast, satellite nowcast, so that is produced in near real time with a little bit less of satellite data. And also looking at weather forecast models that are based on different assumptions, but that could be used to predict whether or not a rainfall will be extreme enough to cause landsliding. So now on the next part of the presentation, I want to move to the monsoon-induced landslide, because these two parts now were mainly focused on large landslide event caused by a relatively short and really intense rainfall, lasting just a few days, where basically when you have 1 meter of rain in 2 days, it doesn't really matter if before the event there was some moisture or not in the ground. What is really important is to know how much it rains in different places, and you will have a rapid saturation of the soil. Of course, when you are in a place where in Nepal you have 3 months of intense rainfall, you cannot just sum the rainfall, or if you really want to understand the landsliding, you will need to include some hydrological process, and we will need to try to understand when the landslide occurs. So we will look at that, and this is mainly the work of Cathy Burrows. You have a picture here if you don't know her. So we started by, I can show you this work, a recent study from Jones and colleagues, where they mapped landsliding in the eastern half of Nepal. And they mapped landslide from the 90s to 2015, to the earthquake, basically. And they could see that the total amount of landsliding, new landslides each year in this area, was strongly correlated with the total amount of monsoon rainfall. So a larger monsoon would cause more landsliding. This is quite reasonable. But they could see, what is interesting is that they could see a large deviation that occur on some years that are after the Gorka earthquake that affected the area. So clearly here there is an effect of weakening of the slope that makes that you have more landslide for the same amount of rain compared to what you would have expected. And then you have also some years where you have much more landsliding, and this could be years where there were reports of large floods, intense rainfall, so some type of, it's sometimes called cloudburst in the Himalayas, so for intense, more or less localized rainfall event within the monsoon. But of course, given that they could not date the landslide, it would not be so easy to define what are the characteristics of this cloudburst in terms of rainfall intensity and in terms of impact on the hydrology. How do they cause the landslide? And also, do the properties of the monsoon-induced landslide and cloudburst landslide differ? To answer this question, it would be much easier if we could separate which landslide occurred during the monsoon, let's say, and which occurred during specifically the cloudburst. And timing landsliding during the monsoon is very difficult from optical imagery, not to say impossible. And that because when you look at a series of, let's say, Sentinel-2 image, you have clear sky image before the monsoon, let's say in April or May, and after in September, October. And then in between, you have a long succession of extremely cloudy events where it's almost impossible to map anything. And only by doing the difference between this pre and post monsoon event, we could map where you have had landslide reactivation, new landslide, etc. But again, just at the monsoon scale, at the seasonal scale, we cannot compare the landsliding to a specific period of rainfall within the monsoon or to relate them to any empirical or physical hydrological model. So to solve this question, we try to timestamp landslides with Sentinel-1. Sentinel-1 because Sentinel-1 is sensitive to surface disturbance. It is undisturbed by cloud cover, and it is acquired every 12 days on 2 tracks globally. So it offers a relatively frequent acquisition. And when you have a satellite overpass, if we know already where the landslides are, and this is, for example, for the moment, this is our approach, that we try to date landslide we already have mapped based on post-monsoon imagery. We can look at the properties of the landslide within, properties of the SAR signal within the landslide polygon where the vegetation has been removed, compare it to the background, etc. And so we can derive different methods based on amplitude, looking at the amplitude relative to the surrounding, looking at the variability within the landslide, looking at geometric shadows, so a large drop because there is no, when you remove the trees in the landslide, you lose the signal that was scattered back by the trees, and you have a zone where there is no refraction. And you can have also double bounds, that is a bit the opposite and this shadow effect, the fact that you can have some rebound here that now are blocked by the trees and going back to the satellite due to the change of geometry. So it's 4 methods, actually, not 3 methods. And this is a work that is in discussion or in review in a natural hazard journal. And when we look at the time series every 6 to 12 days, or you have here each SAR image acquisition, and you have the time series of, let's say, the median landslide minus the median background, or the standard deviation of the amplitude, or the amount of shadows where you see you have no shadows, and then suddenly a large drop, so a large change. And you see these different methods often agree, and they allow to time, by convoluting them with a step function, to time when you have had the largest disturbance and therefore when the landslide should have happened. So we did that on 3 examples, 2 rainfall-induced landslide catalog in Japan and in Zimbabwe, and the earthquake-induced landslide in Nepal, because we want to apply, for example, this method to monsoon area like Nepal. Also, other areas could be Papua New Guinea, for example. And you have the example here in map view. You have one landslide polygon in Japan after the rainfall. And when we look at the SAR signal inside, you see you have a lot of amplitude changes, a lot of increase in amplitude here. And it's sometimes very large increase that could be characterized as shadow based on this threshold. And you have also a change between the pre-event variability and the post-event variability here. And you can see here that in the background, when we look around the landslide, the variation relative to what happened in the landslide are much weaker in average. And when we combine this method, and the double bounce is not shown here, when you combine these 4 methods, we can date about 30% of the landslide. So that's the limit of the method. For most of the landslide on the catalog, we just have not enough clear signal. There is not a clear step change or at least not in several methods. But when we have a multiple response from several methods, we can confidently, within 75% accuracy, attribute a date to the landslide. So of course, and this is a discussion we have now with the reviewer, like, is it enough to date only 30% of the landslide? And what happens if you are not absolutely sure that all of them occurred exactly on this, between these 2 SAR images? Well, I think already at this resolution, it can be quite sufficient for many questions. I will show you some examples. So if we apply this to a large landslide catalog, so the one from Jones and colleagues that I talked about at the start, they mapped more than 3,000 landslides, larger than 2,000 square meters. That's the minimum size where we can apply our methods. And they mapped them between 2015 and 2018, where the Sentinel-1 is active. And you can see here on these different maps, all the white dots are the landslide map by Landsat, by Jones et al. And you have all the color coded dots are the landslide where we could give a timing based on our methods. And you can just see already that it's distributed a bit all across. And you can see also the color is not the same when you look. So we can see that different monsoons don't have the different properties in terms of timing. So if you look here at plots that compare the landslide area versus time during the year, so this is May and this is October, you can see again very different patterns. If we look at 2017, for example, that is the most striking, you see that you have some timing a bit all across the monsoon, but you have a lot of them, a large cluster that all occurred the same week, more or less, or the same 10 days with the precision of the dating. And clearly, it asks the question, is this a cloudburst? Is it a large rainfall event? And clearly, even if we have only 75% accuracy, it's very, very unlikely that this 50 landslide here would all actually be dated at another time and have been wrongly dated here. So with this type of cluster, we can start to probably say something. And we can compare also 2015 and 2018. In 2018, that is that is maybe a normal standard monsoon. We have a relatively small amount of landslide, and they mainly occur near the end of the monsoon without a specific cluster. But in 2015, it's almost the opposite behavior. We have some cluster, and they are very early in the monsoon, and there are very few landslide later in the year. So it asks the question whether this could be due to the earthquake damage, as I showed you that the earthquake has caused more landslide than we would have expected for the amount of rainfall, but they could also have occurred earlier if the slopes were weakened. So of course, to go further, we can look at rainfall data, and this is all preliminary work that Cathy and I are doing here. And we looked for the moment as the GPM, so as the satellite rainfall. And we separate the study area in three bands between Western, Central, and Eastern area. And what you can see in 2017 is that it's very clear again that it's not a coincidence. There is a spatial temporal cluster. Almost all the landslides that are dated in this period here are in this eastern area. And they correspond well to a relatively large peak of rainfall, at least the largest recorded peak by the satellites during this year. In 2015, it's a little bit less clear. There are also some little peaks of rainfall, but it's a little bit less clear. But what we can look is comparing the peak of the rainfall during the cluster and also record the antecedent rainfall, because we have now this effect. And this is what was done by Gabe and colleague. And what you can see when you look at the peak rainfall versus the cumulative rainfall is that in 2018, there is no clear cluster. In 2017, there is this clear cluster. The size of the bubble is the number of landslides here. And in 2015, you have a lot of cluster and a lot of landslide just very, very early in the monsoon with very small cumulative rainfall and relatively small peak daily rainfall. So it's to be continued, but it seems to indicate there is something different here. Okay, I conclude quickly, and we'll finish with a small part on large landslide. So here for this part, I show you that with Sentinel-1 time series, we can give a date stamp of 6 to 10 days for at least 30% of a landslide catalog with about 75% accuracy. And when you look at a catalog where you have hundreds or thousands of landslides, this should be enough to identify spatial temporal cluster and therefore to compare them at term to hydrological forcing. So that's what we will do next, try to refine the rainfall data and maybe include it into simple hydrological model to try to understand what's different between different monsoon years or different clusters. So now to finish with large deep-seated landslides, and it will take a few minutes. So the question is that, the large question I want to discuss here is that what controls a large landslide failure? Are they just related to the trigger effect? So basically to the amount of rainfall, to the dynamic of rainfall, like I showed for the previously for the small ones. And the problem here is that when you look at very large landslide, you have an example here. This is a Jure landslide. It's more than 1 square kilometer. It has depth that reach sometimes 80 or 100 meters in the upper part of the scar here. It buried the full villages here. And it was the largest one that occurred in Nepal in the last 50 years, in eastern Nepal at least. It occurred in 2014 during the monsoon, but it could not relate to the properties of the monsoon, could not be related. Actually, in the plot I showed before from Jones and colleagues, they had to remove the largest landslide of each monsoonal year. Because in some years, at least like in 2014, if you would include them, you would have the total amount of landsliding that was just shifted by 1 order of magnitude. Because the volume in this landslide is as large as all the other ones that are included in the monsoon. So they are disturbing us for this type of scaling relationship when you compare amount of rainfall and amount of landsliding. And in a little bit more detail, I did an analysis by comparing the largest landslide recorded in one monsoon in one catchment in Nepal. So I did that in 2019 for 4 catchments and 7 monsoons. So each point here is relative to 1 catchment and to 1 monsoonal year. And I compare the largest landslide area to the second largest. And what you can see is that most of the time in a landslide catalog for a given monsoon, the largest landslide is 2 to 3 times larger than the second one. And this is what is consistent with the prediction you would make based on the power law distribution that we observe for frequency size distribution. So here, this histogram shows that most of the monsoon, they are between 0.5 and 2 times the prediction. It's very reasonable. But for some events, and including the jury one, we are at 50 times the prediction or 10 to 20 times the prediction here. So we have some large landslides that are much larger than the rest of the distribution. They don't seem to be part of the same statistical distribution. And this could be because maybe they were not related to the same process, not related to the monsoonal rainfall. But then, okay, we can even go in more detail, looking at how the rainfall pattern is correlating to the landslide pattern. And we can see that again with the example of Japan that I discussed earlier. You have here all the landslides that are smaller than 10,000 square meters in black, and the ones that are larger are in green. And when we look at the prediction, it's the color bubble here behind, and especially when we look at the residual, we have a certain residual when we do a prediction based on the rainfall anomaly. If we include all the landslides, the larger landslides, the residual is actually becoming worse. And you can see there is a little bit more dark blue and a little bit more yellow patch here. And when you try to do that in volume, it's even worse. So if you look at the residual here of the prediction of the small landslide volume, it's fair, although it's less good than the small landslide area. But if you look at the large landslide volume, it's really terrible. And this is because, again, the largest landslides are very large volume, and they are not, it's very difficult with this empirical model to predict both the large landslide and the small landslide. So there is a difference with them. And so if they are not caused by the rainfall, or if they don't obey the same rules, what is different with them? Well, I think that probably what is different is that they all may depend on antecedent deformation or structural control. And this is a nice study from Chigira and colleagues in Japan, in the same area, in the Kii Peninsula, where they went and looked at topographic map and high resolution LiDAR DMs in the area where the large landslide happened during the typhoon, during the 2011 typhoon. And what they could see on this place, and they could confirm it in the field also, is that there were already signs of scarps. You can see this linear depression here, and then this little undulation. Clearly, when you would look at the hill slope, there would be several scarps, meaning that the hill slope had already started to deform. So this could be interpreted as long-term cumulative displacement. And Chigira showed that this was present for many of the large landslide in the Kii Peninsula event, but you could also see this type of deformation in large landslide that occur during other events, like during rainfall or earthquakes. So, of course, a big question we want to know is like, how frequent is this? Is it really important? Like, do we need to look for this type of deformation? Well, I did a simple computation here. Looking at the cumulative distribution, so the amount of landslide above a certain size during the typhoon Talas. So the typhoon caused about a bit less than 2,000 landslides. And based on the Chigira work, we know that there are at least 14 that had a proven precursor. And you can see the number of landslide is decreasing as you increase the size. So there is about 100 landslide at this size, like 5,000 square meters. But at 30,000 square meters, there are only 30 landslides. It's only 2%, it's less than 2% of all the landslide, but it's more than 50% of the total volume of the event in terms of sediment. And if you look at the percentage of this landslide that have precursor here, at this size, it's about 50%. So this large landslide that control 50% of the volume, well, half of them had precursors, so they may not have been really driven by the rainfall, but mainly to understand them and to predict them, we should have looked at precursory deformation. And if you go towards even the largest landslide, then for the 10 largest landslide, you have 8 out of them that have this type of precursor. So yes, for the large sediment budget and for the hazard, it's probably very important. And so what to do next? Well, we can look for this type of antecedent deformation, either in high resolution DM or based on modern deformation just before the event when we have a time series of INSAR or image correlation. And this is what was found for the Jura landslide, the one in the Himalaya. Howe and colleagues found that you had almost 10 centimeters of deformation over 4 years that occurred before the landslide failed in 2014. And so this deformation, this continuous creep, can be on much longer time scale illustrative of a rock slope degradation. So the fact that you have the progressive formation of shear zone, of scarp, of folds, and the creep, and then it's only when the landslide, very deep landslide, the bedrock has been crushed, and you have a slope strength that is near the stability limit, that then a seasonal rainfall or an earthquake would be able to trigger it. Whereas any earthquake or rainfall earlier will just disturb it without failure. Okay, so that was the conclusion for this, that large deep-seated landslide, they do not seem to obey the same scaling than the smaller landslides. And probably it's because important part of what controls them is the strength degradation processes, and that these processes, or at least the fact that they are occurring, may be detected based on INSAR or LiDAR DEM. And that's what I will try to do next, quantify how frequent in different catalogs you have this pre-failure deformation, to see whether or not how useful it would be to use one or the other method. Thank you very much for your attention, and yeah, I'm ready to discuss with you. And
great, thank you very much, Odin. That was a really interesting talk. So we've already got a question in the chat. So Brian Wally asks, well, he says, excellent talk, thanks. I learned a lot. Is there similar work for New Zealand, specifically the Southern Island?
Similar work for what, sorry?
I don't know if Brian wants to elaborate on that. Feel free to turn on your microphone.
Ah, for New Zealand, okay.
Yeah, sorry, actually, yeah.
Yeah, I missed the last part. Similar works, so yeah, there are many parts. So in terms of rainfall-induced landslides, I have not. So of course there is a classic work like with the catalogs from Niels Ovdius in 97, but it's not associated with specific storms. It's really long period, like it's mapping all the landslide induced by rain over 10 years. So it's difficult to compare to specific rainfall measurements. So I've not worked too much on that yet. Then, of course, in New Zealand, there may be an interesting work in terms of looking at this large landslide. There are very large landslides in New Zealand, both sometimes caused by the earthquake, like the Kaikoura or previous earthquakes, and all the ones that were present in past rainfall catalogs. So there may be something to do in terms of, looking for preliminary or pre-event, pre-failure marker of deformation. This could be something interesting. Yeah.
Okay, great. Thanks very much.
Okay, yeah, great. So we have another question then. How do you incorporate landscape susceptibility into your analyses? This is quite long, so maybe you have to address it at different points, but the degree of rainfall anomaly occurs on areas with different slope instability susceptibilities. So the landslide signature is a product of both rain and landscape characteristics.
Yes. So in terms of susceptibility, so I can maybe show, yes, the next figure. So this is part of the Gerald paper for the Talas typhoon. And yes, when we try to make a simple empirical model to check how well we could predict the density of landsliding, we find that we would need to use a normalized rainfall anomaly. We would also need to use two different lithology. So if we only looked at the melange, this would be driven by the relatively long-term rainfall, whereas in the volcanic area in red here, you need to use anomaly based on short time scale. So here there is an effect of different lithology with probably different ground, different hydrology. And we also see it in the shape of the landslide occurring in the volcanic areas. They are much more elongated. They often turn into debris flows. And in this correlation, this little prediction, this is also including a slope. So in the patch where we compute the landslide density, we compute the rainfall anomaly and the modal slope. So we look how steep is the area, and we remove all areas with very low slope steepness. So yes, at first order, we need to account for slope and probably somehow for lithology, although it's not clear how we would. You need to look at it case by case. There are no simple indicator that would work in every places. For the satellite product studies, this was just a preliminary study to see if the satellite retrieve rainfall anomaly consistent with the landslide, but we didn't try to do a prediction, so we didn't look so much for susceptibility, except for checking that we could remove the anomaly. So if the satellite found a large anomaly offshore or on a flat area, we would not consider it a false alarm, because obviously we would consider it would not cause landsliding. So I see there are tons of very long questions in the talk. So
yeah, I can take the next one then. So Jeffrey asks, what are your recommendations for sort of localized landslides which cannot be identified with the Landsat resolution? What tools are used to know the wetness of the soil, I guess it means, using satellite?
Okay. Wetness of the soil. Some people are working on some specific satellite product that gives the soil moisture. Although there is a lot of discussion whether or not it's relevant for landslide, because it's very superficial soil moisture. So it doesn't really say how much it has infiltrated or not. I'm not sure what is meant by localized landslide. If it's small landslide, because there is a mention of Landsat resolution, well, now some of the catalog I showed you before actually were not mapped with Landsat. They were mapped with Sentinel-2 at least 10-meter resolution, but very often with planet imagery that is at 3-meter resolution, sometimes with Earth photos or a mixture of Google Earth high-resolution images. So yeah, that's the point. Of course, when we want to look back in time for longer time studies, we may need to use lower resolution image. So it will only be relevant for large relief landscape where you have relatively large landslides.
I can take the next question, maybe. Yeah. So it's a question by Sihan Lee. So first, very excellent talk, extremely interesting. I want to ask whether the time stamping landslides for Nepal datasets is published or released.
Yeah, so it's ongoing. So as I showed, now you can go on the natural hazard and earth system science to look at the method. So the method is in a preprint. It's going to evolve a little bit. Like the double bounds that I mentioned now is something we add in the review process. But you have some example and you have some statistics for the result. But this part where we apply it to the different catalogs is not published yet. The method has not even finished review. So we will publish them. It's the next paper that Cathy will work on. What is available, however, is the catalog of the landslide mapped from the 90s to 2018 by Jones.
Okay, and I can take the next question by Jonathan Perkins. So exciting talk regarding using satellite data for your rainfall anomalies. I noticed that the rainfall total for Typhoon Talas was much less than what you measured from radar. Do you think that the measurement frequency from satellites fails to capture some of the high-intensity rainfall bursts that radar captures? And do you think this might contribute to less robust anomaly relationships?
Yeah, I totally agree. That's a nice spot, and we do that. We see that for many events. So this is here, for example, where you see that the rainfall is only up to 500 millimeter, whereas the radar was at more than 1,000. So clearly, the satellite capture much less rainfall. It does probably come from the fact that you have infrequent analysis at high precision, let's say. And so you often get biased. It sometimes also comes from the fact that they try to readjust the satellite based on gauges. Although I doubt it's a problem in Japan. So probably it's related to the fact they cannot capture all the high intensity rainfall. But what is interesting is that when you normalize by the long-term extreme climatology, the extreme climatology is also much weaker. You see the 10-year return rainfall, according to the satellite, is only 300 to 400 millimeter. Whereas in the radar, based on the ground radar, we found also something on the order of 1 meter. I mean, we found that the 10-year return rainfall here in this zone was more than 1 meter. That's why the anomaly is very weak here. So that's what I was explaining here with the case of Taiwan. We also have a lot of, if you look in absolute value, if you compare different satellite products, they really give very different things with very different mean rainfall across the areas. And that's why the anomaly is less good clearly when you use the satellite than the radar or in situ data, but going to anomaly remove part of the bias. I think that's the important message.
Thank you, Odin.
Okay, then I can take the question next. So thank you so much for your talk. Sorry, this is a long question. It's by Mong Han. In the first part about saprolite properties responding to extreme rainfall pattern, what is the time scale do you think the saprolite would need to adjust the property according to long-term rainfall pattern? And sorry, you can go on, then I can say the next part.
I do a first part on that. Yeah, it's a good question. I have not worked in detail in that. There are references in the paper, in the GRL paper I mentioned. There's a reference to the few modeling work that were done based on the distribution of rainfall and stability of the slopes. And I'm not exactly sure what were the time scale, but it's probably relatively long. And therefore, obviously, we use a 10-year return rainfall, but it's not in 10 years or in even a few tens of years. It's on a much longer time scale that you will have a series of large landslide events that will make the soil evolve. So there is an implicit assumption that is that if we measure now the recent climate, extreme climatology, it has not changed too much, let's say over maybe 1,000 or a few thousand years. That is the time you need to adapt the landscape, to co-evolve the landscape. And on one comment on that is that it could be that in some landscape we would need to take different anomaly, but clearly I don't think we will ever have enough data to constrain very long return event that may be on the same time scale. To give an example, in Japan, the last time there was in this peninsula, so there was a smaller event in 2004. But the last time there was a very large landslide event on the same scale of the one of 2011 was in 1884, so 140 years ago. So clearly this very large landslide event that may have a strong impact on the landslide, on the landscape, evolution, they occur rarely. And even with the best rainfall data, you will not get better than the 50-year return time scale. So somehow we need to have this assumption that the climatology has not changed too much. But then probably what we see in the radar data in this climatology is that it's very affected by the orographic effect. And this orographic effect is due to the fact that typhoon most of the time arrive from the south and they hit this mountain range. So this probably has not changed in thousands of years. So I think the poor quality of that we see in many different cases may more be related by either the type of the storm. As I said, short storm are difficult to capture, or the fact also that depending when they happen, during the 20 years of analysis, the satellite constellation may have been more or less robust because the number of satellites has changed. And also sometimes you are lucky, you have the active radar and microwave covering very well your storms, and sometimes no, it passed just on the edge and you have not so many good measurements during the storm. So I would rather look in this direction.
Okay, so and the second part of the question is, do you think this timescale could vary in different latitude and climate? And could this be the reason why your models don't work everywhere due to incomplete long-term extreme rainfall data, or a change of timescale needed for saprolite to adjust to climate pattern? Yeah,
well, so I think I answered a little bit this with the long discussion, or I hope. And it could be a part, but first it will be really hard to check, and second, I think there are more direct problem just in the acquisition of the rainfall event and of the rainfall climatology I think this is more the problem. And here the latitude and longitude could play a little bit because the satellites, the property, how they overpass in different zones can be a bit at play. Yes.
Okay, yeah, thank you. I can also take the second question, which is again by Shihan Lee, which is another quick question is the 10-year return value, is it based on 1-day precipitation?
Yeah, it's based on, no, the short answer is no. And the slightly longer answer is that it's computed at a given time scale. And it depends. So in this event, I found that the most relevant time scale was the 2-day time scale and the 2 hours time scale in the different lithologies. Of course, in the other zones, it's difficult to know whether it's a very intense, short, localized burst of rainfall or long rainfall, because sometimes the anomaly can be strongest on long time scale or short time scale. So for the satellite, for the global analysis, we looked at 3 hours, 12 hours, 48 hours, and 96 hours. So I compute the anomaly for all the different time scale, and then I just take the best anomaly. So of course, there is also an implicit assumption that if there was a strong anomaly at short or long time scale, it could be causing the landsliding. And but the method could be, you could compute the anomaly at any time scale. So then it's just that as you go to longer time scale, you start to run into the problem that, yeah, if you would compute an anomaly for 1 week, the problem is that during a week of rainfall, you have also drainage, and you start to have the problem that you should not only look at rainfall, but have an hydrological model.
Okay, thanks.
Okay, I actually have a quick sort of more basic question. I don't know if that's okay.
Yeah.
I was wondering, I mean, this might apply to actually a lot of what you've talked about already, but you mentioned a bit about the clustering of landslides. Could you say something about repeat events within the same sites, and how the fact that, you know, you might continuously fail at the same locations, and how this then factors into kind of the assessments that you've made, or whether you consider one location to be one event?
Yes, that's a very good question. So there is a little bit of, just to start on the background, there is a little bit of literature on that in New Zealand, from relatively old literature, where they looked at repeating storms on pasture land, so not forested. And they could see that when you had a large storm that caused a lot of landslide, in the year after, even when you had large rainfall, you had almost no landslides. So clearly here you would have the effect that you had a depletion and a change of susceptibility. Then you have the opposite case. I showed the example of the earthquake in Nepal, where you have an earthquake. The earthquake caused tens of thousands of landslides, so a huge amount of landscape disturbance. But the next monsoon caused more landslide, not less. So depending on the landscape setting, typically, I think on relatively gentle landscape where you have fixed soils, it's only the soil that can fail. And therefore, if you have a lot of landslide failure, you may be kind of depleted for the next event. But when you are in more active ranges, where you have a steep mountain ranges with relatively fractured bedrock, regolith at many scales, here I don't think that this concept that there would be a limited stock of available slopes to fail is really relevant, and you will just fail different slopes. And so for the rainfall in my event here, there are only 2 places where in Japan and in Taiwan somehow. In Taiwan, for example, we see that there are large landslide events that occur very frequently, and after 2009 there have been large typhoon trigger landslide events. The same after the Chichi earthquakes, there were a lot of typhoon that caused landsliding, and we didn't see so much less landslide. So, but in the detail exactly, would we think that after a typhoon we have more or less susceptibility is not so easy to say. I think there is not an intuitive explanation. There have not been so much new work after this work in New Zealand. So the fact is that you need to have the landslide exactly at the same place, right? If you look, I can show you this example. Yes, here we have a lot of landslides here. But in 2004, there was another event, but it's here. It's not really the same place. It's around here. So of course there is a little overlap, but then it starts to be not so easy to compare. Same thing, you heard maybe some weeks ago, there was a large disaster in Brazil. And this is the same area than the one in 2011 here, but it's not, it's just the next city. So I think I need to check on the map, but it may be a bit more around here. So if it's not the same zone, what can you say? Yeah, so.
Thank you. So we have one more question in the chat. This is sort of quite a big question, this one.
Yeah.
Do you think there is a relationship between climate change and landslides? The IPCC report indicates a reduction in landslides.
Yeah, I think it's also an important research challenge, and that clearly there should be a relationship. If we think that this anomaly effect is a strong predictor for landsliding, given that the rainfall become more extreme, but that the landscape is used to a certain type of extreme climatology, we should see more landslides. As it's implied by the end of the question, if the IPCC predicts an increase of especially extreme precipitation, I'm not sure a change in the mean precipitation would be so important, but it should cause more landsliding. I don't know exactly on what is based the first part of the sentence, saying that the IPCC is indicating less landslides. There have been a nice review by Gariano and Buzzetti, I think in 2016, it's an Earth Science Review paper that looked at many publications. So it's a bit of meta-analysis. And in different parts of the world, they found that it's complicated because in some places, the global warming is mainly increasing landsliding because you have melting of permafrost. In other places, you have more intense rainfall. You may have more landslide because of that. In some places, we see less landsliding indeed. So it's a bit not clear everywhere, and there can be a compensation of different effects. You have also the increase in maybe wildfire that could change the susceptibility of the slope and makes more debris flow after them. So I think generally I would expect more landslide, and but I don't know if the IPCC has a very clear view on that. There have not been so many studies yet, so I think there is more to do on that. Yeah.
Okay, thank you very much, Odin. So lots of really good questions, and I'm sure this could go on for a long time, but I think perhaps it would be a good idea to stop this there. Thank you. Please sort of accept our thanks, Odin. That was an excellent talk, and thank you very much for answering all of our questions. And thank you to everybody as well for participating in this.
Yeah, no, thanks a lot.
Yes,
and
thank you.
Keep going with the nice seminars also on the organizing team.
Yes, thank you very much. Okay.